efficiency for its 7-har turbine. Aeroderivative gas turbines can also be used in combined cycles, leading to a higher efficiency, but it will not be as high as a specifically designed industrial gas turbine. They can also be run in a cogeneration configuration. The exhaust is used for space or water heating, or drives an absorption chiller for cooling the inlet air and increase the power output, technology known as turbine inlet air cooling. Another significant advantage is their ability to be turned on and off within minutes, supplying power during peak, or unscheduled, demand. Since single-cycle, gas turbine-only, power plants are less efficient than combined-cycle plants, they are usually used as peaking power plants, which operate anywhere from several hours per day to a few dozen hours per year, depending on the electricity demand and the generating capacity of the region. In areas with a shortage of baseload and load-following power plant capacity or with low fuel costs, a gas turbine power plant may regularly operate most hours of the day. A large single-cycle gas turbine typically produces 100 to 400 megawatts of electric power and has 35–40% thermodynamic efficiency. Industrial gas turbines for mechanical drive, edit. Industrial gas turbines that are used solely for mechanical drive or used in collaboration with a recovery steam generator differ from power generating sets in that they are often smaller and feature a dual shaft design as opposed to a single shaft. The power range varies from 1 megawatt up to 50 megawatts. These engines are connected directly or via a gearbox to either a pump or compressor assembly. The majority of installations are used within the oil and gas industries. Mechanical drive applications increase efficiency by around 2%. Oil and gas platforms require these engines to drive compressors to inject gas into the wells to force oil up via another bore, or to compress the gas for transportation. They are also often used to provide power for the platform. These platforms do not need to use the engine in collaboration with a CHP system due to getting the gas at an extremely reduced cost, often free from burn-off gas. The same companies use pump sets to drive the fluids to land and across pipelines in various intervals. Compressed air energy storage, edit. Main article, compressed air energy storage. One modern development seeks to improve efficiency in another way, by separating the compressor and the turbine with a compressed air store. In a conventional turbine, up to half the generated power is used driving the compressor. In a compressed air energy storage configuration, power, perhaps from a wind farm or bought on the open market at a time of low demand and low price, is used to drive the compressor, and the compressed air released to operate the turbine when required. Turboshaft engines, edit. Main article, turboshaft. Turboshaft engines are used to drive compressors in gas pumping stations and natural gas liquefaction plants. They are also used in aviation to power all but the smallest modern helicopters, and function as an auxiliary power unit in large commercial aircraft. A primary shaft carries the compressor and its turbine which, together with a combustor, is called a gas generator. A separately spinning power turbine is usually used to drive the rotor on helicopters. Allowing the gas generator and power turbine forward/rotor to spin at their own speeds allows more flexibility in their design. Radial gas turbines, edit. Main article, radial turbine. Scale jet engines, edit. Also known as miniature gas turbines or microjets. With this in mind, the pioneer of modern microjets, Kurt Schreckling, produced one of the world's first microturbines, the FD3/67. This engine can produce up to 22 newtons of thrust, and can be built by most mechanically minded people with basic engineering tools, such as a metal lathe. Microturbines, edit. Main article, microturbine. Evolved from piston engine turbochargers, aircraft APUs or small jet engines, microturbines are 25 to 500 kilowatt turbines the size of a refrigerator. Microturbines have around 15% efficiencies without a recuperator, 20 to 30% with one, and they can reach 85% combined thermal electrical efficiency in cogeneration. External combustion, edit. Most gas turbines are internal combustion engines, but it is also possible to manufacture an external combustion gas turbine, which is, effectively, a turbine version of a hot air engine. Those systems are usually indicated as EFGT, externally fired gas turbine, or IFGT, indirectly fired gas turbine. External combustion has been used for the purpose of using pulverized coal or finely ground biomass, such as sawdust, as a fuel. In the indirect system, a heat exchanger is used and only clean air with no combustion products travels through the power turbine. The thermal efficiency is lower in the indirect type of external combustion. However, the turbine blades are not subjected to combustion products and much lower quality, and therefore cheaper, fuels are able to be used. When external combustion is used, it is possible to use exhaust air from the turbine as the primary combustion air. This effectively reduces global heat losses, although heat losses associated with the combustion exhaust remain inevitable. Closed-cycle gas turbines based on helium or supercritical carbon dioxide also hold promise for use with future high-temperature solar and nuclear power generation. In surface vehicles, edit. Gas turbines are often used on ships, locomotives, helicopters, tanks, and to a lesser extent, on cars, buses, and motorcycles. A key advantage of jets and turboprops for airplane propulsion, their superior performance at high altitude compared to piston engines, particularly naturally aspirated ones, is irrelevant in most automobile applications. Their power-to-weight advantage, though less critical than for aircraft, is still important. Gas turbines offer a high-powered engine in a very small and light package. However, they are not as responsive and efficient as small piston engines over the wide range of RPMs and powers needed in vehicle applications. In series hybrid vehicles, as the driving electric motors are mechanically detached from the electricity generating engine, the responsiveness, poor performance at low speed and low efficiency at low output problems are much less important. The turbine can be run at optimum speed for its power output, and batteries and ultracapacitors can supply power as needed, with the engine cycled on and off to run it only at high efficiency. The emergence of the continuously variable transmission may also alleviate the responsiveness problem. Turbines have historically been more expensive to produce than piston engines, though this is partly because piston engines have been mass-produced in huge quantities for decades, while small gas turbine engines are rarities. However, turbines are mass-produced in the closely related form of the turbocharger. The turbocharger is basically a compact and simple free-shaft radial gas turbine which is driven by the piston engine's exhaust gas. The centripetal turbine wheel drives a centrifugal compressor wheel through a common rotating shaft. This wheel supercharges the engine air intake to a degree that can be controlled by means of a wastegate or by dynamically modifying the turbine housing's geometry, as in a variable geometry turbocharger. It mainly serves as a power recovery device which converts a great deal of otherwise wasted thermal and kinetic energy into engine boost. Turbo compound engines, actually employed on some semi-trailer trucks, are fitted with blow-down turbines which are similar in design and appearance to a turbocharger except for the turbine shaft being mechanically or hydraulically connected to the engine's crankshaft instead of to a centrifugal compressor, thus providing additional power instead of boost. While the turbocharger is a pressure turbine, a power recovery turbine is a velocity one. Passenger road vehicles, cars, bikes, and buses, edit. A number of experiments have been conducted with gas turbine-powered automobiles, the largest by Chrysler. More recently, there has been some interest in the use of turbine engines for hybrid electric cars. For instance, a consortium led by micro-gas turbine company Blade on Jets has secured investment from the Technology Strategy Board to develop an ultra-lightweight range extender, ULRA, for next-generation electric vehicles. The objective of the consortium, which includes luxury car maker Jaguar Land Rover and leading electrical machine company SR Drives, is to produce the world's first commercially viable and environmentally friendly gas turbine generator designed specifically for automotive applications. The common turbocharger for gasoline or diesel engines is also a turbine derivative. Concept cars, edit. The first serious investigation of using a gas turbine in cars was in 1946 when two engineers, Robert Kafka and Robert Engerstein of Carney Associates, a New York engineering firm, came up with the concept where a unique compact turbine engine design would provide power for a rear-wheel drive car. After an article appeared in Popular Science, there was no further work beyond the paper stage. Early concepts, 1950s/60s. In 1950, designer F.R. Bell and chief engineer Maurice Wilkes from British car manufacturers Rover unveiled the first car powered with a gas turbine engine. The two-seater Jet 1 had the engine positioned behind the seats, air intake grills on either side of the car, and exhaust outlets on the top of the tail. During tests, the car reached top speeds of 140 km per hour, 87 miles per hour, at a turbine speed of 50,000 rpm. After being shown in the United Kingdom and the United States in 1950, Jet 1 was further developed, and was subjected to speed trials on the Jap Highway in Belgium in June 1952, where it exceeded 240 km per hour, 150 miles per hour. The car ran on petrol, paraffin, kerosene, or diesel oil, but fuel consumption problems proved insurmountable for a production car. Jet 1 is on display at the London Science Museum. A French turbine-powered car, the SOS McGregor, was displayed at the October 1952 Paris Auto Show. It was designed by the French engineer Jean-Albert Gregor. The first turbine-powered car built in the US was the GM Firebird I, which began evaluations in 1953. While photos of the Firebird I may suggest that the jet turbine's thrust propelled the car like an aircraft, the turbine actually drove the rear wheels. The Firebird I was never meant as a commercial passenger car and was built solely for testing and evaluation as well as public relation purposes. Additional Firebird concept cars, each powered by gas turbines, were developed for the 1953, 1956 and 1959 Motorama Auto shows. The GM Research gas turbine engine also was fitted to a series of transit buses, starting with the Turbo Cruiser I of 1953. Starting in 1954 with a modified Plymouth, the American car manufacturer Chrysler demonstrated several prototype gas turbine-powered cars from the early 1950s through the early 1980s. Chrysler built 50 Chrysler turbine cars in 1963 and conducted the only consumer trial of gas turbine-powered cars. Each of their turbines employed a unique rotating recuperator, referred to as a regenerator, that increased efficiency. In 1954, Fiat unveiled a concept car with a turbine engine, called Fiat Turbina. This vehicle, looking like an aircraft with wheels, used a unique combination of both jet thrust and the engine driving the wheels. Speeds of 282 kilometers per hour, 175 miles per hour, were claimed. In the 1960s, Ford and GM also were developing gas turbine semi-trucks. Ford displayed the Big Red at the 1964 World's Fair. With the trailer, it was 29 m, 96 feet long, 4.0 m, 13 feet high, and painted crimson red. It contained the Ford-developed gas turbine engine, with output power and torque of 450 kilowatts, 600 HP, and 1,160 Nm, 855 pound-foot. The cab boasted a highway map of the continental US, a mini kitchen, bathroom, and a TV for the co-driver. The fate of the truck was unknown for several decades, but it was rediscovered in early 2021 in private hands, having been restored to running order. The Chevrolet division of GM built the Turbo Titan series of concept trucks with turbine motors as analogs of the Firebird concepts, including Turbo Titan I, C1959, shares GT304 engine with Firebird 2, Turbo Titan II, C1962, shares GT305 engine with Firebird 3, and Turbo Titan III, 1965, GT309 engine. In addition, the GM Bison gas turbine truck was shown at the 1964 World's Fair. Emissions and fuel economy, 1970s/80s. As a result of the U.S. Clean Air Act amendments of 1970, research was funded into developing automotive gas turbine technology. Design concepts and vehicles were conducted by Chrysler, General Motors, Ford, in collaboration with RE Research, and American Motors, in conjunction with Williams Research. Long-term tests were conducted to evaluate comparable cost efficiency. Several AMC Hornets were powered by a small Williams regenerative gas turbine weighing 250 pounds, 113 kilograms, and producing 80 HP, 60 kilowatts, 81 PS, at 4,450 RPM. In 1982, General Motors used an Oldsmobile Delta 88 powered by a gas turbine using pulverized coal dust. This was considered for the United States and the Western world to reduce dependence on Middle East oil at the time. Toyota demonstrated several gas turbine-powered concept cars, such as the Century gas turbine hybrid in 1975, the Sports 800 gas turbine hybrid in 1979 and the GTV in 1985. No production vehicles were made. The GT24 engine was exhibited in 1977 without a vehicle. Later development. In the early 1990s, Volvo introduced the Volvo ECC, which was a gas turbine-powered hybrid electric vehicle. In 1993, General Motors developed a gas turbine-powered EV1 series hybrid, as a prototype of the General Motors EV1. A Williams International 40 kilowatts turbine drove an alternator which powered the battery electric powertrain. The turbine design included a recuperator. In 2006, GM went into the EcoJet concept car project with Jay Leno. At the 2010 Paris Motor Show, Jaguar demonstrated its Jaguar CX-75 concept car. This electrically powered supercar has a top speed of 204 miles per hour, 328 kilometers per hour, and can go from 0 to 62 miles per hour, 0 to 100 kilometers per hour, in 3.4 seconds. It uses lithium-ion batteries to power 4 electric motors which combine to produce 780 bhp. It will travel 68 miles, 109 kilometers, on a single charge of the batteries, and uses a pair of blade-on micro-gas turbines to recharge the batteries, extending the range to 560 miles. 900 kilometers. Racing cars, edit. The first race car, in concept only, fitted with a turbine was in 1955 by a U.S. Air Force group as a hobby project with a turbine loaned them by Boeing and a race car owned by Firestone Tire and Rubber Company. The first race car fitted with a turbine for the goal of actual racing was by Rover, and the BRM Formula One team joined forces to produce the Rover BRM, a gas turbine-powered coupe, which entered the 1963 24 Hours of Le Mans, driven by Graham Hill and Richie Ginther. It averaged 107.8 miles per hour, 173.5 kilometers per hour, and had a top speed of 142 miles per hour, 229 kilometers per hour. American Ray Heppenstall joined Howmet Corporation and McKee Engineering together to develop their own gas turbine sports car in 1968, the Howmet TX, which ran several American and European events, including 2 wins, and also participated in the 1968 24 Hours of Le Mans. The cars used Continental gas turbines, which eventually set 6 FIA land speed records for turbine-powered cars. For open-wheel racing, 1967's revolutionary STP Paxton turbo car fielded by racing and entrepreneurial legend Andy Granatelli and driven by Parnelli Jones nearly won the Indianapolis 500. The Pratt & Whitney ST6B62 powered turbine car was almost a lap ahead of the second-place car when a gearbox bearing failed just 3 laps from the finish line. The next year the STP Lotus 56 turbine car won the Indianapolis 500, pole position even though new rules restricted the air intake dramatically. In 1971 Team Lotus principal Colin Chapman introduced the Lotus 56B F1 car, powered by a Pratt & Whitney STN6/76 gas turbine. Chapman had a reputation of building radical championship-winning cars, but had to abandon the project because there were too many problems with turbo lag. Buses, edit. General Motors fitted the GT30X series of gas turbines, branded Whirlfire, to several prototype buses in the 1950s and 1960s, including Turbo Cruiser I, 1953, GT300, Turbo Cruiser 2, 1964, GT309, Turbo Cruiser 3, 1968, GT309, RTX, 1968, GT309, and RTS3T, 1972. The arrival of the capstone turbine has led to several hybrid bus designs, starting with HEV1 by AVS of Chattanooga, Tennessee in 1999, and closely followed by AVS and ISE Research in California, and Design Line Corporation in New Zealand, and later the United States. AVS turbine hybrids were plagued with reliability and quality control problems, resulting in liquidation of AVS in 2003. The most successful design by Design Line is now operated in 5 cities in 6 countries, with over 30 buses in operation worldwide, and order for several hundred being delivered to Baltimore and New York City. Brescia, Italy is using serial hybrid buses powered by microturbines on routes through the historical sections of the city. Motorcycles, edit. The MTT turbine superbike appeared in 2000, hence the designation of Y2K Superbike by MTT, and is the first production motorcycle powered by a turbine engine, specifically a Rolls-Royce Allison Model 250 turbo shaft engine, producing about 283 kilowatts, 380 bhp. Speed tested to 365 kilometers per hour or 227 miles per hour, according to some stories. The testing team ran out of road during the test, It holds the Guinness World Record for most powerful production motorcycle and most expensive production motorcycle, with a price tag of US $185,000. Trains, edit. Main article, gas turbine locomotive. Several locomotive classes have been powered by gas turbines, the most recent incarnation being Bombardier's jet train. Tanks, edit. The 3rd Requiremakt Heeres Development Division, the Heereswaffenamt, Army Ordnance Board, studied a number of gas turbine engine designs for use in tanks starting in mid-1944. The first gas turbine engine design intended for use in armored fighting vehicle propulsion, the BMW 003-based GT101, was meant for installation in the Panther tank. Towards the end of the war, a Jagdtiger was fitted with one of the aforementioned gas turbines. The second use of a gas turbine in an armored fighting vehicle was in 1954 when a unit, PU 2979, specifically developed for tanks by C.A. Parsons and Company, was installed and trialled in a British Conqueror tank. The Stridsvagn 103 was developed in the 1950s and was the first mass-produced main battle tank to use a turbine engine, the Boeing T-50. Since then, gas turbine engines have been used as auxiliary power units in some tanks and as main power plants in Soviet/Russian T-80S and US M1 Abrams tanks, among others. They are lighter and smaller than diesel engines at the same sustained power output, but the models installed to date are less fuel efficient than the equivalent diesel, especially at idle, requiring more fuel to achieve the same combat range. Successive models of M1 have addressed this problem with battery packs or secondary generators to power the tank's systems while stationary, saving fuel by reducing the need to idle the main turbine. T-80S can mount 3 large external fuel drums to extend their range. Russia has stopped production of the T-80 in favor of the diesel-powered T-90, based on the T-72, while Ukraine has developed the diesel-powered T-80U and T-84 with nearly the power of the gas turbine tank. The French Leclerc tank's diesel power plant features the Hyperbar hybrid supercharging system, where the engine's turbocharger is completely replaced with a small gas turbine which also works as an assisted diesel exhaust turbocharger, enabling engine RPM-independent boost level control and a higher peak boost pressure to be reached than with ordinary turbochargers. This system allows a smaller displacement and lighter engine to be used as the tank's power plant and effectively removes turbo lag. This special gas turbine /turbocharger can also work independently from the main engine as an ordinary APU. A turbine is theoretically more reliable and easier to maintain than a piston engine since it has a simpler construction with fewer moving parts, but in practice, turbine parts experience a higher wear rate due to their higher working speeds. The turbine blades are highly sensitive to dust and fine sand, so that in desert operations air filters have to be fitted and changed several times daily. An improperly fitted filter, or a bullet or shell fragment that punctures the filter, can damage the engine. Piston engines, especially if turbocharged, also need well-maintained filters, but they are more resilient if the filter does fail. Like most modern diesel engines used in tanks, gas turbines are usually multi-fuel engines. Marine applications, edit. Main article, Marine propulsion. Naval, edit. Gas turbines are used in many naval vessels, where they are valued for their high power-to-weight ratio and their ship's resulting acceleration and ability to get underway quickly. The first gas turbine-powered naval vessel was the Royal Navy's motor gunboat MGB 2009, formerly MGB 509, converted in 1947. Metropolitan Vickers fitted their F2 forward/3 jet engine with a power turbine. The steam gunboat Grey Goose was converted to Rolls-Royce gas turbines in 1952 and operated as such from 1953. The Bold-class fast patrol boats Bold Pioneer and Bold Pathfinder, built in 1953, were the first ships created specifically for gas turbine propulsion. The first large-scale, partially gas turbine-powered ships were the Royal Navy's Type 81, Tribal class, frigates with combined steam and gas power plants. The first, HMS